Okay. Good. All right. Thanks everybody for joining us. My name is Jamie Marsden. I'm a business development manager with Emerson. I'm based out of Houston, although as you can tell, I don't have a Houstonian accent. I'm originally from South Africa. I've been in the States about 20 years. I have about 35 years now of experience in the analyzer world. So I lived a lot of my life in refineries. I've been to many countries around the world in refining, so I've seen a lot of regulations and a lot of very, very interesting measurements that get done. Sometimes these measurements are fantastic for the customer because they're optimizing a process, or they're helping you do something quicker. And sometimes it's the opposed, where it's sort of a hostage situation where you have to do a measurement for a regulatory body, which is not necessarily a bad thing, because obviously we want the environment to be clean. We live here. We obviously want to have a clean planet. So I'm going to run through a couple of little slides first, just to say who Emerson is. Basically, we were founded in 1890. Pretty big company, 83,000 employees worldwide. Okay. We have 2.4 billion annual sales, in software, and $16 billion for the fiscal year of 2020, which was good because of COVID, everybody was impacted. So that's a couple of little things, and obviously this presentation is available, so you'll be able to see this just for later review. There is also a keynote, a message from that we actually had from Mark this morning. I don't know if anybody was at the keynote. Mark had a couple of words. So this, again, you could go through on your own. And then we do have a booth, and I will say I don't have my beast of a analyzer there because it's a bit big for that little booth. But we have a virtual unit online, and obviously you can contact me if you wanted to have a demo or even look at one. If you're in the Houston area, the manufacturing facility is in Houston, so we actually make them there. So there is other ways. What we do have at the booth is some PRV measurements, and some safety measurements being done that are much smaller units. All right. So, quick show of hands, because I'm going to talk. Is everybody familiar with this regulation, this flare regulation that I'm going to talk about, the BTU measurement in the flare? Is most people familiar with it? I'm going to talk about it anyway again. And then I'm also going to talk a little bit about GCs. Is everybody familiar with a gas chromatograph? Okay. Because I can talk a little bit about how a gas chromatograph works. If it's of interest, I don't have it in the slide, but I can try. I do have a slide where I'm talking comparison-wise against other measurements. So I can try to give you a 1,000-foot view on that, because I lived in the world of those other measurements too. I spent 20 years with Thermo Fisher, so I'm very familiar with their technologies of doing this measurement. So I'll try it. I will not give you the salesman pitch of buy ours and don't buy theirs. I'll be very straightforward and across the table of what the measurements do and what the differences are in these analyzers. Let's just talk a little bit about the requirement. And the reason I'm bringing this up is this came out originally. Actually, it was 2016 they started with this. It took them a couple of years. And it was eventually implemented in January 30th, 2019. I'm not aware of any refineries that are still that don't have to do this, that were sort of grandfathered in or have some other way out of it. We just dealt with a customer, one of our older customers actually in the Houston area that had an older system that wasn't in compliance, but they had a little bit of a negotiation going with the EPA, and they were able to use that until they got their new unit. So basically, this regulation, because there's a couple of different federal regulations, okay? Some of these measurements started out all the way from Rule 1118, all the way from California back in 2000. I think that was 4 or 5, could even be earlier than that when that rolled out. And you had to start monitoring certain things. Now you have the HRVOCs that you have in Houston. Those are, so every sort of state or refinery has maybe a slightly different measurement they do, but they all have to follow the federal regulations too. So part 63 was specific to this word right here, BTU. So my heritage is actually English, although my accent is South African. And I always like to joke that you thought you got rid of the British, but they still exist in one of your major measurements here, right? And this specific rule, we'll have a look at in a minute, was basically stating that they wanted to measure the BTU in the flare to make sure that it's above a certain destructive capability. How they came up with the number they have, you can go ask them, because I don't know if anybody actually knows. They just came up with this number of 98%. So I'm assuming they did some calculations and said 98%, you should be good. Nobody's going to get any problems if there's stuff that gets out over that. Anyway, so the rule actually states, and it's written out again here, but basically it said that within a 15, and this is pretty standard for a lot of the EPA measurements, within a block of 15 minutes, you have to report the BTU. And it needs to be above a certain limit. Way back in the old days, before they had to do this measurement, a lot of the refineries would have these towers and they would have these viewing platforms that they view the flare. I don't know if you guys have ever seen those, or if you guys are from refineries and seen those, but basically if there was an event happening in a refinery, and again, nobody wants an event happening. Nobody wants to send something to the flare that's, that's going to cause an issue, but sometimes when you're making product, you don't have an option. Something goes wrong, you got to get rid of it. So somebody would actually be out on the viewing station and be like, watch, if somebody said, hey, we're watching the DCS, watching the SCADA, there's a problem on this unit, the butane unit's got a problem, we have to dump. Somebody would actually go out and watch the flame, watch the flare. And they would then do assist gas, or they would do steam, trying to get the steam up to get the heat up to basically quench, because it was called the smokeless. You don't want to have any smoke there. And if you go to some of these spots, I don't know, maybe it's calmed down a little bit now, but I've been in some of the refineries where they have EPA parking bays. And there's guys that drive up in the EPA car and they sit there and they watch the flares. And then if they see something, they're allowed to go in, and pretty crazy. But there's other ways of doing it. I'm just saying that does happen too. So, all of this is mentioned in here. And you can read it, you're probably familiar with this, but basically you had to measure in 15 minutes, and then you had to come up with you had to have, you had flow measurements being done, and then you also had to come up with basically with an action plan, right? And here we talk about the destructive capability, 98%, and so on, so on, so on, so on, so on. So all of this has pretty well been said. And the reason why I still talk about this ruling is because it rolled out to EMAC and MONMAC. It rolled out to the ethylene producers and the miscellaneous flare who doesn't fall into ethylene, polymers and these other guys, they fall. So these regulations started in 2016, rolled out in 2019. I need to go speak to, because I haven't seen the latest, I need to go speak to Troy over at Spectrum if he knows if EMAC is even rolled out yet, or is it still in process, and MONMAC, when's that coming, or they are sort of in process, but they're not enforced, because those were the next targeted. So at the end of the day, it's almost like anybody that operates a flare is going to have to monitor the flare. So they based the original EMAC, MONMAC regulations loosely on these. But if you're an ethylene producer, or you're in a chemical plant, or you know that those flares are a lot cleaner than what's in a refinery. A refinery is the worst case scenario. So, but you still have to do the measurement. There is a couple of miscellaneous refineries, or should I say miscellaneous chemical plants, that I think don't have to do the measurement if they can prove what the process is, and there's nothing that can hurt anybody, right? So it's a little bit of gray area, and especially now because the administration's changed. So, you know, things change with administrations. All right. And because this is a GC talk, I'm going to talk about GCs. So one thing I want to mention here is that 15-minute rule. You know, whenever the 15-minute rule came in, nobody had any issues with 15 minutes, because 15 minutes is a long time to do a measurement. But what a lot of the operators started doing, they said, you know what? I can get rid of that guy that's standing out on that platform and looking at that flare if I can optimize my flare. So if I have to measure the BTU, and I can do a measurement in the BTU, and I can tell what the BTU in the flare is very quickly, then I can optimize the assist gas and the quenching. So basically, instead of putting a whole lot of steam up there to get it hot and not knowing how much money I'm spending doing that, I can control this now and save money. So this is where certain analyzers came into their own, okay? Because a gas chromatograph, if you have a familiarity with a gas chromatograph, the best thing about, the nicest thing about a gas chromatograph, or should I say the number, but what I say is the best thing is it's one of the only technique that I'm aware of that does a measurement without an interference. What it does is it separates out all of the components and measures them one by one by one by one by one. Okay, the other techniques don't do that. Okay, mass spec, it has to take all of these components that will be on top of each other in some cases. Okay, if you look at a mass spec, mass 28, N2 is, nitrogen is 14 mass, 2 nitrogens, which is measured in mass specs, 28, overlaps with almost everything that is important, methane, EO. So what happens in that case? They have to run multiple gases and fragment everything out, okay? But they're quick. So that's their advantage. Ours is we're slow because we have to do this. So how do we compete against the mass specs? How do we compete against the calorimeter? Okay, guys familiar with calorimeters? Okay, so a calorimeter is another device I'll show it up in a minute that can measure the BTU. So you have these 3 devices. Let's make it simple: calorimeter, mass spec, and GC. Basically, these are the guys that are doing the measurements. Calorimeter, depending on what type you have, basically only measures BTU. There's no composition. You cannot go back and find out what happened in the process, what unit had the issue. You could only get BTU. So what they do is a lot of times they marry up a calorimeter and a gas chromatograph. Calorimeter gives a quick BTU, and GC gives the composition, so they can go back and see what happened where. Okay, but now you've got 2 analyzers. Mass spec does BTU and does composition. So 1 analyzer. Okay, what I'm going to present to you today is our GC that does both as well. It does the composition, but it also does the BTU. And it does the BTU, depending on the composition, within 1 to 2 minutes. So you actually get what you call a fast GC measurement, which is not normal in the field. It's where it is normal is in turbine control, custody transfer, that type of place where they need to be optimizing certain things. You can do BTU, but it's never fast BTU in a GC. It's never been a prerequisite or something that's ever been needed to be done in the refinery. Okay. So requirements in this are, so if you have sat in on any of the mass spec talks, or you've heard there's 2 mass spec vendors outside here, Thermo Fisher and Extral, they have their units there. They also have to fall under this table 13. And basically table 13 is a specification table. It talks about the list of components that have to be measured, and it talks about the precision and the accuracy of these components, and it goes through a couple of different things. Okay. Then it also talks about this, 10% of the calibration gas over a certain time period. So basically, you can't just put any old analyzer in there and then say, oh, we're meeting reg. The EPA is going to want to know you're doing this, you're doing validations, you're doing quarterly validations, how accurate is the analyzer, where's the calibration of this unit, that type of thing. Okay. That's what this really talks to. Here's I don't think I've got any competition in here but if they are, I'm not killing anybody here, I'm just showing some pros and cons of each technology. So gas chromatographs, I'm talking about the big guys here. It's basically you have your ABB, you have CEMS, Yokogawa, and Emerson. Okay. If you're in a refinery or in a plant or somewhere, you would have seen these guys. Okay. So I give a little bit of a spiel over here and talks a little bit about what components, composition. But if you look at the bullet points, which are sort of more important, I have some tick marks for the good points, and I have some little reds for the bad points. Just having a look at the time. So here we have this keyword, slow analysis for flare BTU control. And I'm going to address that in a later slide. Typically for gas chromatographs I'm talking about. But they can be mounted outside. They can be configured to do multiple streams. And the familiarity is the biggest one right here. Gas chromatographs have been in refineries for a very long time. A lot of people are familiar with the technology. Mass spectrometers. Here's the main suppliers again, Thermo Fisher, Extral, Schneider. Thermo Fisher and Extral are actually here. And this is some history. Refineries have typically steered away from mass spectrometers. And that's not me saying that. Like I said, I spent 20 years with Thermo Fisher. I struggled to get a mass spectrometer into refineries. The reason for that is they are considered an advanced technology, which means there's very little familiarity with them in refineries. Some of the most key people in your refinery are the guys that are taking care of the analyzers. If you don't have guys that can take care of those units out there doing measurements, you're going to have a real problem. So, and again, I say historically, because the mass specs have moved on from that. They tend to have more available parts, and they tend to. You go talk to them, they'll probably say their uptime is whatever for 99% for the year type of thing. But again, this was one of the problems. The other problem is they do require a shelter. So if you're in a refinery or when you're doing a measurement, space is premium. Some of those refineries are full. You can't just put shelters all over the place. Some of them already have analyzers in there. You can't just stick more in. Good point about them, though, is they do very fast measurements. Typically, you can get a measurement done in 30 seconds. Very good for control. And then we have the Wabi index calorimeters. COSA, Yokogawa, and Hobrecht. COSA is here. So again, a couple of things. They typically require a shelter, though you can get them mounted outside. They do a fast BTU. They cannot be configured to do multiple streams, and they cannot give you any composition analysis. So that just gives you sort of an overview of the measurements that have been done for this 40 CFR. If you have any questions specifically on the slide, just raise your hand and we can do them at the end. So here's a typical flare measurement, just showing you, here's a gas chromatograph here, here's our gas chromatograph doing a measurement. What it's going to be doing, as you can see, it's going to be measuring the supplemental gas going up into the flare. There is some other Emerson products here. This one is actually, we have at the booth. So this is basically showing you if you have, it's a PRV, basically showing you if there's any leak happening on a valve. And then some other wireless devices here. And then there's a Fluenta device. Fluenta, we partnered with a lot on doing the flow to the flow measurement. They're also here. So if you look at the Fluenta booth, GE has a big booth. GE does the same. Okay, they're measuring the flow. That's one of the other requirements. All right, so this is going to get a little bit into the technical part of things. So how do we do the measurement? How's it possible that a gas chromatograph can do this? So what we did is we took the GC, and we said, how can we make this GC do two measurements? Well, if you put two GCs in the place and you did one GC, sample came in, went to the one GC, then went to the other GC, and this GC just did a quick measurement, and this did a longer measurement, you could get it done. But now you have two GCs. So what we decided to do, and we have now the capability of doing what we call 4 clocks. Think of the clocks as being GCs in a way. This is the brains. This is the processors inside the GC. When you are doing an analysis, your processor is doing a lot of work. The processor is getting all the information. It's basically processing it. It's basically calculating everything out. It's then doing the software part of it, and it's then transmitting out. So it's typically a busy device. So what happens if we put two processors in there? So we can separate out. One can do one thing, one can do another thing. Then you get limited by size inside the GC because, again, I think everybody said they had a basic understanding of gas chromatographs. Gas chromatographs have valves inside of them and columns. That's how they separate out. Okay. The column, if you went in and looked at a process gas chromatograph, the columns are pretty short, a couple of feet. If you went in and looked at a lab, if anybody came from the lab, they can have 20, 30 feet columns. 50 feet.
50 meter, actually.
50 meter.
Yeah.
Let's keep going. But again, like I said, you are separating out the mixture. You've got a mixture of gas. You bring in this mixture. How do you separate it out in a GC? You send it through a column. The column, there's capillary columns. There's different types. There's porous columns. There's basically filled columns. They work on boiling point, melting point. There's different types of columns. Okay. What the job of the column in very layman terms is to basically take the hydrocarbons and they basically will separate out the components through them. I always compare it to when you go shopping. When I get home from doing these trips, my sons are older now, so she doesn't have an excuse, but when they were younger, she'd had them for a week. It was like, you go do the grocery shopping. So I would load up the car. I get to the pay, and I don't know of any grocery store, if you know one, tell me, that you just walk through with the car and you're done. You unpack it all. So this is basically what we're doing in a GC. We're unpacking the hydrocarbons one by one, and then we take them to a detector and it reads them. But the unpacking part takes time. Okay? Those other technologies don't unpack. Basically, they do, they do calculations within software to separate out. So we basically designed some additional clocks. We put some additional detectors in there. and we put some additional valves in there, and we basically designed it so that it was 2 GCs in one. One sample comes in, gets split, one goes to one set of columns and valves, another one goes to another set of columns and valves. This one would have a longer set of column and valves. I'm just giving you in layman's terms, and that would give you your analysis of, and I'll show you in a slide coming up of how long that takes. The other column set has been geared specifically just to do BTU. So it has a different column set in it and a different measurement time. All right, so here's a couple of different detectors being shown. We have a thermal conductivity detector would be inside of there. A thermal conductivity detector is basically a detector that measures anywhere from typically from 30 ppm all the way up to 100%. These other detectors, an FID and an FPD, will do low-level hydrocarbons and low-level sulfurs if you had to do that. Okay. All right. So then we get to this word over here that we call parallel chromatography. What parallel chromatography basically means is that we have the same thing I just mentioned. We have 2 sets of measurements happening through the GC, each going to their own processor. Excuse me. So now we have this where we measure 2 standard solutions. So we have two standard solutions to meet the compliance. Why do I say 2? Because there's a number of refineries that don't necessarily have benzene, and some other refineries have benzene. So we typically have to ask you, do you have benzene? Do you not have benzene? So that we can configure this unit to measure correctly. So here's a little overview. So benzene is typically going to be a longer measurement, typically more towards the 10 to 12 minutes. And without benzene, it's a little bit of a shorter measurement because benzene is problematic. I wouldn't say problematic, it just takes a long time to come out of a GC. Okay. The typical setup will have 4 thermal conductivity detectors, 2 carrier gases. Okay. There's the pack columns and there's some valves, and it does require instrument air. So, and the sample is a vapor. We haven't even spoke about sample conditioning, and that's not part of this talk. I think the mass spec guys and the other guys will tell you the same. Probably the most important part about any of this measurement is your sample conditioning. So the sample coming out of flare is typically pretty horrible. It can be full of anything. It can have sulfurs in it, water in it. So when you're putting this in, if you're pricing out this package, and you're responsible for saying to the company, okay, I think we need to look at these technologies, and that's great. You spend $200,000, $100,000, $300,000 on an analyzer. The actual solution is probably going to be $1 million. Because you might need a shelter. That's a lot of money. Then you get into the requirement of doing the sampling, which can be your most expensive part. So you've got to deal with a sampling expert. Emerson, Extral, Thermo Fisher, the suppliers of the equipment are not sampling experts. The separate companies that do that. Okay, so it gets to be a very expensive exercise. I think when I was talking to the guys, some of the guys that have been out there and been doing this, I don't know if we have any flare guys here this week. I don't know if we have any, I don't know if they're here, I'm talking about, they go to different shows, but the guys actually design the flares. They will tell you, typically for them to implement these solutions, it was between $1 to $2 million. So it's very expensive if you, the good thing is that you probably already are falling under the other CFRs and having to measure the sulfurs. Because sulfur's been around for a long time. You have to measure the SO2s. You have to measure the H2S going out of the flare. So you probably have existing sampling and conditioning systems. Maybe you can tap off from those. Yes, sir.
Question. What benzene level are you targeting in the flare? Are you at the ppm or the ppb?
I'll have it on a next slide. It'll show you a level. Yeah, so again, be very cognizant of the other requirements that are not just your GC. So if you have a look here, here's, we actually, on this one, it's up to 5% benzene. So this is getting more into, sometimes the guys sitting in the room are GC guys and they're familiar with the measurement. So it would be a miss of me if I didn't explain a little bit how the measurement gets done. I'll try to keep it very high level. What we do is we're going to do, like I said, we're going to do a BTU measurement on the major components. So what we do is we individually measure nitrogen and oxygen as one. Okay? Carbon dioxide, hydrogen, methane, ethane, ethylene are all measured individually. Okay, so we have to have a specific column set for that. Again, if you know anything about GCs or have an idea, you know the quickest way to do a GC measurement, if you wanted to measure something quick, is a measurement of backflush. What that means is when you take a whole lot of components, you might send them to one column set, and then you send them to the detector all together. This is called backflush. Why do you do that? If somebody decides that they don't want to measure C3, C4, C5, C6, C7s, because it's inconsequential in their process, it's so small, they'd rather have the speed, you can design a column set and have a valve that switches that basically lets everything else get through, holds on to those for a while, they eventually juggle their way through, get to the valve switches, and it sends them back to be detected. And you can get those backflush components out in 30, 40 seconds, but it's one peak. And in this specific case, it says C63 plus. You've heard of that term? C4 plus, C5 plus, C6 plus, C7 plus. Anything plus means everything up to C7 is being individually measured, and everything after C7 is being one measurement, okay? So why do we do this? We can't measure these individual components and try and do it in that 1 to 2 minutes. It's impossible. We have to bunch up so that we don't have to wait for them to come out. Because in GC theory, the heavier the hydrocarbon, the longer it takes to elute through the GC. And I put that in parentheses because process GCs can manipulate how the hydrocarbons are flowing. They can put different column sets, different valves, and switch things around. So they're moving some in, they're moving some out. They do some magic. So this is how we do the BTU measurement in the 1 to 2 minutes. Which is called virtual GC2. It's the same GC, it's just going through a different set. Measures the individual components. Isopentane and the M-pentane, it'll lump together as a C5. So that's going to be your 8 to 12 minute analysis. So what's going to happen is your system's going to be updating every minute, 1 to 2 minutes, depend again. I say 1 to 2 because if you had a very simple composition in the flare, you could probably do it much quicker, 1 minute. If it was more complex, we have some doing 90 seconds. Okay. So people say, well, 90 seconds, 1 minute, that's great, 2 minutes, okay, but the mass spec does it in 30 seconds. So talking to refineries and talking to the customers, that 30 seconds is fantastic, but they can control in 1 to 2 minutes. 1 to 2 minutes is fine for them to control. They cannot control in 10 minutes. It's too late. So these guys, if you can give them a 1 minute, a 90-second analysis, they say that's enough for my control. Because again, why wouldn't they just go to the mass spec? Well, we start talking about, again, complexity of the measurement, complexity of the analyzer. A gas chromatograph uses 1 calibration gas. How many calibration gases does a mass spec use? 1 for each component. So, and I've been, again, like I said, I lived in the world of mass spec. I went to Shell Norco 1 year. And customer had been having some issues with his mass spec. So we went and looked and we managed, we fixed it out. I was an application engineer at that time. And then we went to calibrate. Customer hadn't checked calibration gases in a couple of weeks. And that's usually not an issue. The problem is when you start putting butanes in some heavies, they can only put 4 or 5 pounds in a bottle. After a month or 2, you may not have 4 or 5 pounds in the bottle anymore. So this is why you've got to be aware of the solution you're putting in, because you have to calibrate these analyzers. And if you are on one solution and are sitting with 20 calibration bottles, you have safety concerns, you have concerns about getting the bottles in and out, costing concerns. So that's why I said there's all these plays that happen, all these things are happening out there that you've put in, or you advise this is a technology we need to use. So you have to be aware of the questions. Sometimes you don't know the questions to ask. You know, how much does this analyzer cost to run a year? Well, you got this analyzer, you got a box. If it goes wrong, you put the spares and you're done. Well, how much is the actual analyzer cost to run? How much does my gases cost? You know, what's the downtime? What's all these things? You know what I mean? So there's different questions. All right. And then we combine the two, and this is basically a combined analysis done. So, just want to see how we're doing for time. About 5 minutes. Okay. So again, just showing you, different carriers, different trains, and different detectors. And that's if we add benzene, it adds its own train. So a train, if you don't know what a train is, basically a train is just the method of analysis. This is what it looks like. 2 bottles, like I said, 1 calibration bottle, 1 carrier bottle, and then you can put them into a shelter too, like that, on the MTS side. I'm speeding up a little bit because there might be a couple of questions. And then we have all the support material on our site for this. Okay, VOC, because I had to slide this in. So a VOC measurement is something else that you're doing on your sites. Some type of VOC is typically being done. This specific unit we just installed is doing VCM, Vinyl Chloride. What's of interest, and you'll see on the next slide, is this sample conditioning system. This is doing 20 samples and has a pump. The reason it has a pump is this is ambient air monitoring, so it's pulling in samples. We put this unit into the customer site and it worked fantastic, and then the customer called us up and said, yeah, your analyzer is not working, as a problem. So the guys went out there and had a look, and fence line monitoring had something that happened, and basically the sample point had ended up in this is in Louisiana, in the swamp, and basically filled up this pump and all these with water. So, but I wanted to mention this because a gas chromatograph can also do fence line monitoring, and there's quite a few out them doing that. But same model. This is the VCM peak. What's nice about VCM is you typically just measure VCM in air, so it's not a case of multiple peaks being seen. You've just set up your column set to do this measurement, and this measurement is being done. This is 85 seconds, so 110, 2 minutes, 1.5 minutes analysis time per stream. There's other ways to do VCM. I've seen them because I've been out there and looked at them. But again, if you guys have familiarity with gas chromatographs, it's possible to do this measurement on a gas chromatograph. It's been done. I think we've got like 2 or 3 minutes left. So if there's any questions. Yes, sir.
So may I ask you, when you say VOCs, it's a big term to use. What specifically are those VOCs that you benzene? So is it benzene? I've heard that normally people refer VOCs normally benzene, toluene, xylene. Is this under that umbrella, or you're talking about methane?
Yeah, again, it would depend on what. So yeah, BTEX, correct, is, as you said, benzene, toluene, ethylene, and xylene. The problem with those type of measurements is I wouldn't say it's a problem. They're actually a federally mandated measurement right now in LNG because of the fact that we export it. It's not a US regulation, but it's an export regulation. So those measurements get done actually in pipeline. If you had a plant, yeah, you could do those too. Typically, what you would do with those three, you can do it two ways. You can either individually measure them, which means a much longer measurement, or you just have BTEX measurement, which is all three of them, and a limit on the BTEX. Specifically, they're going to be like under 2 ppm. I think that's one that's fair. But yeah, you can lump those as one, and you do benzene, ethylene chloride, something else. Something that is, it depends on your plant. Depends on if you're Formosa plant, depends on what is going to be your BTEX.
When you're talking about that backflush method, is the backflush, I guess, sent through after the component you're looking for passes through the detector?
Yeah, so what's going to happen on a standard GC system, you have a sample that comes in and you have one valve, which is called a sample valve. It injects a sample loop or sample, then goes through one column set, then gets typically to the next valve is called it's in backflush valve. So those components that you want to backflush are being restricted by this column set. The other components flow very freely through the backflush valve that goes to the next column set, and it's all based on timing.
Right.
This switches and sends this back this way, and it gets another flow path through another side of that same sample valve.
Right. Okay.
You had mentioned in the VOC example that the sample system was filled with water. You mentioned earlier